Okay, so now let's talk about extending the trigonometric functions so they work for all angles, right? I mean, we think of angles as being rotations, so we can sure rotate a lot more than just between 0 and 90 degrees. And we'd like the trig functions to work for more than that, not just on triangles. So let's talk about how to extend the trigonometric functions so they work for arbitrary angles. Well, you'll see there are some points where they become undefined, just like the originals do, but I'll show you how it works. Okay, so here's the basic idea. Here I've drawn what's called the unit circle. So this is just a circle of radius 1 centered at 0. It's a little bit hard to see here depending how big your screen is, but this is a 1, this is a -1, a 1, and a -1 here. And what you've got to be able to do here is we know that if we start with one of our original definitions, right, we start with an angle between 0 and 90 degrees, we know how to define the sine and the cosine, right? The sine is the ratio of opposite to hypotenuse, for example, right? But in the unit circle, just like in the previous picture, our hypotenuse is equal to 1. And so therefore, the ratio opposite over hypotenuse just becomes equal to the length of the opposite side. And so in fact, the sine of a given angle theta is just the length of this edge here on this right triangle, and that is just its y coordinate, right? Right there. So that's where I write this down, that sine of theta is equal to the actual y coordinate that lives on the unit circle here. Likewise, the cosine, remember, that was that ratio of adjacent over hypotenuse. And again, the ratio of adjacent over hypotenuse, because our hypotenuse is equal to 1, is just actually equal to the value of the adjacent, no matter what it actually is. And of course, this adjacent side length is just the x-coordinate. It's just the x-coordinate of this point up here. So that's what I mean by writing cosine of theta is equal to x and sine of theta is equal to y. That's where these equations come from. Because in this case, on the unit circle, the sines and the cosines can be interpreted as actual lengths of these sides, right? Now, if you look over the old definitions in terms of ratios, you would see that the tangent can be rewritten as sine divided by cosine. And I'll just explain this once for the tangent, and you'll see how the rest of them work, right? So remember, by definition, the tangent of a given angle theta in our original picture was just the ratio of the opposite side over the adjacent side. But the sine is the ratio of the opposite side over the hypotenuse. And the cosine is the ratio of the adjacent side over the hypotenuse. And what we see when we carry out this division is that these hypotenuses cancel, and we get back the original tangent. So this is why we can define the tangent in this way. For similar reasons, the cotangent can be defined as the ratio of cosine divided by sine. Secant of theta is 1 divided by the cosine, and the cosecant of theta is 1 divided by the sine. So these are all things that you can work out. And what I'd like you to do, okay, is your first little assignment to bring into class on Wednesday is the following. You bring in strings of equations just like this. I'm not even going to write it on the board. Bring in a string of equations that justifies this. So we saw this one. We have sine of theta is equal to opposite over hypotenuse divided by adjacent over hypotenuse is equal to opposite over adjacent, which gives us the tangent, right? Verify these remaining equalities in the same way, starting from the definitions of these things as opposite over hypotenuse and so on. So do that. Bring that in. That will be, it's a test of your understanding, but it's also a test that you're actually watching this, because I'm taking time out of my day to do this. A lot of time. This takes more time. This isn't, I know this looks like beautiful, natural, but this takes time. This is not, whatever. Anyway, so here's the point. What's going on here? What was the next thing? I totally derailed myself here in this talk. Let me get to the point. Okay, yeah. And so basically the point is that once we've nailed down cosine and sine, we can figure out the definitions of these remaining functions right here, right? So it's enough just to nail these two down, and then we'll have the trig function defined for all the rest of them too. You get a few weird places that we'll talk about later, but we'll take it from there. Okay, and so what's nice about this definition, just to find the cosine of theta to be the x-coordinate and the sine of theta to be the y-coordinate, is that it allows us to define it not just for acute angles, but for any angle at all, right? So let's say I want to look at an angle like, I don't know, 243 degrees, right? So 243 degrees means that I'm rotating past 90, past 180. I'm not getting all the way up to 270, so I'm sitting somewhere around here, let's say, right? So this is my angle. Let's say this is 243 degrees, right? In this case, to figure out what the sine and cosine of this angle are, right, what do we see? We need to find the x and y coordinates of this point. And although I can't tell you off the top of my head exactly what this angle is, you'll have to plug into a calculator. There are a couple of things that we can predict, okay? Just by looking at this, we know that the cosine of 243 degrees, that's equal to the x-coordinate of this particular point. And so therefore, we can see that it's a negative number. It's bigger than 0, but it's smaller than 1. And likewise, the sine of 243 degrees is also negative. All right? And I didn't draw this quite right. It should go down a little further. It should go down here. But the point is that both of these, since both the x and y coordinates are negative here, the sine and the cosine are also negative over there. And what you notice though is that fundamentally though, this isn't that different from the original sine and cosine functions. The only difference is the quadrant we're in will possibly change the sign of one or the other, right? If instead I've been looking to find like what is the cosine of 100 degrees and what is the sine of 100 degrees, well in that case my angle isn't going quite as far. It's only going up to here and it's stopping. And for this pair of points, x and y, I see that the cosine is negative and the sine is positive. Now at this point, we don't have very many good techniques for computing these functions exactly for any arbitrary angle. In fact, ultimately, the calculator is going to be your tool anyway. I'll talk about the specialized angles that we actually can compute precisely next time. But let me just also point out that we can also extend this trigonometric definition to negative angles as well, right? So let's say I'm looking at the cosine of negative 43 degrees, right? I want to compute the cosine of negative 43 degrees. Well, I just go over negative 43 degrees, which is just, it's just going the clockwise direction now, about 1/8 the way around the circle, not quite. And I see that this is positive. And if I look at the sine of negative 43 degrees, however, that is negative. And again, I can do further rotations. What we'll notice is that if I do another 360 degrees, I'm coming back to my original value of sine and cosine. And again, we can do these same definitions. Instead of using degrees, we can use radians. That's fine as well. But this is the definition of the trig function for an arbitrary angle. You just read off the x and y coordinates associated with that angle. That will give you your cosine and sine. And from there, you can figure out tangent, cotangent, secant, cosecant. Next up, I'm going to show you some particular examples of this that we can do for particular triangles. Okay, so all of the angles that we can compute exactly, unlike the ones I showed you where we can only use calculators to guess, and the calculator guesses are based on something I'm not even going to get into. I can't get into in this class. But there are certain values at which certain angles at which the trig functions, all of them can be computed precisely, perfectly. And you need to be able to do these for all sorts of types of web-assigned problems and on tests. But all the values at which they can be computed are based on, they're either degenerate easy values, which I'll talk about, or they're based on one of two triangles. The 45-45-90 triangle, which I've drawn here, and the 30-60-90 triangle, which I've drawn here. And 30-60-90 refers to the interior angles, right? You have a small 30-degree angle, a 60-degree angle, and the 90-degree angle, which is the right angle, and here you have the 45-degree angle, the 45-degree angle, and the 90-degree angle. I have actually done these in units of radians, though, so if you're able to zoom in and see, 30 degrees is actually pi over 6 radians, and 60 degrees is pi over 3 radians. In any event, if I choose my base side to be 1 on a triangle of this type, I can automatically infer that the opposite side will have length 2, and this side right here will have length square root of 3. Likewise, if I choose a base side equal to 1 on my 45-45 triangle, then I know obviously the other side is going to be 1, and this length will be equal to not 2, which was a typo, but the square root of 2. And so before I actually go on to apply this, let me explain the why of this. So the reason for this is as follows. It's easier to see it with the 45-45-90 triangle. So we know simply because these two angles are same that the triangle that we're dealing with here has to be an equilateral. That means that this has length size 1 and this has length size 1. I mean isosceles, excuse me. This has length 1 and this has length 1. Now, by the Pythagorean theorem for right-angled triangles, this means that 1 squared plus 1 squared has to be equal to this h squared. And this reduces to the fact that, h squared is equal to 2, and therefore h must have a length square root of 2 in this case. The one for the 30-60-90 triangle is one step harder, but you can still understand it just starting from scratch. It's not something you have to memorize. So here's the basic idea. If I take my 30-60-90 triangle here, and I make a second copy of it, and I plant it right next to it, what I will discover is that this angle is 60, this angle is 60, and now this combined angle here also adds up to 60 degrees. And so since all the interior angles are equal inside of this triangle, all of the side lengths must be equal as well. In other words, I have an equilateral triangle. That means that this side here, which I know to be 2, because it's double the length of my original 1, this side out here must also be 2. So that's why I see that I go from here to here. See that this length is 2. Once I know that this side length is 1 and this side length is 2, I again use the Pythagorean theorem in a more indirect way to find the length of this final side here. And I discovered that final side has to be equal to square root of 3 after a little bit of algebra. See that algebra up there? Just do that, okay? And that's where these facts come from.